네, 이번 시간에는 세계 최대 양자 지원 프로그램 싱가포르 사례에 대해서 들어보는 시간을 갖도록 하겠습니다. 이번 강연에는 NQSN 싱가포르 큐컴스 테크놀로지스트 하오킨님의 강연을 들어보도록 하겠습니다. 영어 자막이 지원되니까 편하게 들으시면 될 것 같습니다. 자, 그러면 양자 시대를 준비하는 싱가포르 사례에 대해서 들어보도록 하겠습니다.
Hello everyone, my name is Hao Jing from National Quantum Safe Network Singapore. I'm affiliated with Center for Quantum Technology and the National University of Singapore. Thanks for the organizer to invite us to join this event.
As well as efforts has been made in Singapore in the quantum safe direction. As you notice or not, today many technology around us are based on the laws of quantum physics. From the transistor in the laptop to the laser used for optical communication that enable high-speed internet, and the GPS in your mobile phone. All this technology bring us a lot of convenience in our life, and they are all thanks to the foundation of the quantum physics. In a certain sense, we are already living in the quantum area. You may heard that very recently we are transitioning in the second quantum revolution already. So what it is about? So for the second quantum revolution, scientists discover more interesting quantum property such as superposition, entanglement, which will enable many technology that cannot reach by the traditional classical physics. It's including the ultra precision for the quantum methodology and sensing, and high performance, high computation power for the quantum computation, and a certain simulation of the quantum physics with quantum computing and simulation, and ultra safe quantum communication. All this technology can be potentially used wider range of in our life, including infrastructure, environmental, energy, military defense, finance, medical, and etc. So in the second quantum revolution area, the quantum technology supply chain is even now being built up. From the quantum computer, quantum communication, its components, and the end user, all these things are being built up to enable different technology taking advantage of quantum property. Moreover, the Nobel Prize in Physics from last year was awarded to 3 pioneer scientists who work on the experiments with the entangled photons. Their pioneer work shows that the capability of quantum information processing. It also indicates for the coming years what's likely the technology trending direction is. So what's the second quantum revolution or quantum technology has a connection with the topic of today's webinar on the quantum security and what's the impact from the quantum technology. So to answer this question, maybe we go back to the beginning of the cryptography history. So cryptography means to hide secrets in Greek words. So its history can trace back to 100 BC, the Caesar cipher, and it did play an important role in the history. The Ingeman machine you may heard that it's a turning point for the Ally to crack its secrets. And more recently, more advanced and modern cryptography tools has been invented. This including the DES, the public key cryptography key system scheme, the symmetry key cryptography scheme, scheme. All these modern cryptography tools has enabled us to do confidential thing through the internet. So from your online transaction to your ATM machine withdrawal or your online buying, all this process or procedure all involved all this cryptography process. And what's the next step for this thing? And are they really safe? So maybe in the quantum world, the answer may be not that certain. That will come to the invention of the several quantum algorithms that can potentially break those cryptography systems. To run the quantum algorithm, we need a quantum computer. So what is a quantum computer? What's the difference from the classical computer? So in classical computer, we encoding information with binary bits 0, 1. You can see it as a coin head and tail. So it's always either the head or either the tail. These two sides is not correlated, but we can also make copy of these coins. On the other hand, for the quantum bit, it will never be 0 or 1. On the other hand, it will be the superposition for these two states. It can be the head and tail at the same time. And these two things are correlated. This is somehow the entanglement between these two quantum bits. And we cannot copy the quantum bit perfectly without additional information. So by using the quantum property of the quantum bits, such as superposition, entanglement, it opens a new way for information processing. And it also opens the door for some quantum algorithm that we cannot find the analog in classical world, but it can potentially accelerate the efficiency to solve certain computation problem. So on the right is the image of the superconducting qubit experiment setup that was built up in Singapore. So let's go back to the algorithm that I mentioned, that why such algorithm put potential risk to today's cryptography system. On the left one is the Gouverneur quantum algorithm. So it somehow speed up the efficiency of searching some data. So for this algorithm, it has potential application to reduce the complexity to cracking the symmetry key crypto system. So, however, such algorithm may not speed enough to put really risk to the symmetry key system. So for example, just double the size of the AES key, it can help you to resist such kind of algorithms attack. On the other hand, I mentioned that the public key cryptography is based on the factoring a big number. The hardness of such problem, however, can be efficiently resolved by such algorithm. So Shor's algorithm helps to do the factoring of big number much more efficiently, which somehow put a risk to our today's public key cryptography. Almost all the asymmetric key methods are in a risk once such algorithm can be realized in a quantum computer. So this somehow bring up our today's topic for the webinar. how we can move to the quantum safe cryptography direction. So what is the impact of the quantum computer towards all this public key and symmetry key scheme? So there's estimation for this from some report from the community that we can see in face of the quantum computer. Today, even the 2048 RSA public key scheme is no longer safe, while the symmetry key is somehow still be safe by increasing its key size. So most of the public key cryptography is no longer secure under the threat of the quantum computer. And such threat could be very serious. All this public key based technology could be broken once the quantum computer is realized. This including the data breach in the financial sector and personal data, threatening the message that's exchanged on the internet, and the integrity of the digital document, the cryptocurrency, and what more important is that the harvest now, decrypt later attacks, that the attacker can potentially save the data that transmits over the internet today and decrypt it once the quantum computer is realized. So what is the real threat of the quantum computer that on the today's cryptography system? So here is a chart to show that the development of the quantum bits that has been realized in the quantum computer for the past 2 decades. From the beginning 2 qubits, now we can reach to 100 level of qubits. However, the research shows that if we want to run the Shor's algorithm and really crack the today's 2048-bit RSA, we still need 20 million noise qubits. But it also shows that if large-scale quantum computer can be realized, it will really threat the modern cryptography system. So what's the quantum threat timeline? So whether we should worry about the quantum computer today or in the future. So the X plus Y theory from Professor Mosca in Canada give us somehow the answer. So in his equation, the Y stands for the mitigation time and the X stands for the data security time. And that stands for the large-scale quantum computing building time. If X plus Y is smaller than that, then we are in a safe position that quantum computer will not have big threat on our data. However, if X plus Y is bigger than that, then we need to worry about it. So, in short, the quantum threat is not immediate. It will be a medium or long-term threat. So, deploy quantum safe cryptography and quantum safe communication in time will be a good strategy. So quantum safe means that our cryptography system remains safe even if large-scale quantum computer became available. Let's come to our webinar's main topic on the quantum security. So what are the elements to build up of the quantum safe security? We have the post-quantum cryptography, PQC, quantum key distribution, QKD, and random number generation, RNG. So for the PQC, its security is similar to the public key algorithm, but however, it's designed in a way that it can secure still against the quantum algorithm attack. So its security is still based on the computation assumption. QKD and RNG, they are security based on the laws of physics. So for QKD, it can reach so-called information theoretical security, in which no matter how strong the computation power is, its security still holds. So PQC, QKD are the efficient solution to be quantum safe, and the RNG will provide the true quantum needs entropy source to support the quantum safe application. So let's go to more details on the post-quantum cryptography. So it's also based on the hard mathematical problem, which are very difficult to solve, and even for the quantum computer. And its security is against some known quantum attacks. But future cryptanalysis can still impact the security. The main advantage of PQC is that it can fit our current ICT world very well because it uses similar principle. We just need to change or update the algorithm in software. So it has a good succession of the public key scheme and digital signature key establishment. These are the fundamental part of our current cryptography world. So you may heard about the NIST PQC standardization efforts. So basically, it's select for different PQC algorithm to be standardized as the standard for the PQC algorithm. So right now we are advanced to the fourth round, and hopefully we will see some PQC standard in the coming years. So what about QKD? What is principle? So in short, the quantum channel will exchange the quantum state, and with the cease of the classical channel with additional information processing, QKD key can be produced as a symmetry key resource for different application. So for the encryptor and decryptor, so people can use the key resource from the QKD to combine with their crypto system to encrypt their data. So basically the QKD is for establishment symmetry key, and its security on the channel is protected by the laws of quantum physics. So far these are the two main approach for the quantum safe technology. So how about Singapore's initiative in quantum technology? So in fact, Singapore has steady investment over 2 decades on the different direction of quantum technology. Its story starts from 2002, and with some milestone event. First one is the Center for Quantum Technology was created in 2007, and very recently, quantum engineering program was also created to promote the quantum technology to be industrialized and to be applicable to our lives. So in the development of the quantum safe, there are some free space QKD demonstration as early as back to 2006. NUS has already successfully demonstrated the QKD distribution over the urban and daylight environment in Singapore with some quantum entanglement photon source. There are also try work of QKD over the production grade fiber network, including the NUS Intel Cybersecurity R&D Lab launched in 2016 to support QKD try in Singapore, and the quantum entanglement distribution has been successfully distributed over the Intel's existing fiber network. So what's more, how about the satellite-based quantum communication and quantum internet? So here is a photo of the Spooky, a nanosatellite that's doing entanglement distribution, and it was launched in the International Space Station in 2019. Another milestone for quantum technology in Singapore is the setting up the quantum engineering program. Its vision is to contribute to solve national problems, build up the quantum technology supply chain, and explore interesting use cases. And its ambition is to build up the quantum ecosystem that coordinate the basic research, applied research, and encouraging the innovation and technology transformation, hatch the quantum startup, and build up the quantum facility. So thanks to the quantum engineering program, QEP, under the QEP program, 3 national platforms has been initiated regarding to different quantum technology. For the quantum communication and security, National Quantum Safe Network program is set up, and I'm from this program. For the quantum computer, National Quantum Computing Hub has been set up, targeted on the quantum computing and its processor. For the quantum sensor, the National Quantum Fabless Foundry for the fabrication of the quantum chips and sensor has also been set up. Since I'm from the NQSN, I will give you more details on the project. It's a national platform that is hosted by the security, that is NUS. So we have the project member from also Nanyang Technology University and Fraunhofer Singapore. So in the National Quantum Safe Network platform, our vision is for the government and the industry to progressively explore the quantum security and the quantum reliance solution. Our main technology will be rely on the quantum key distribution, in which QKD network will be deployed over the fiber optics networks. So we envision the network topology from point to point to international QKD, and which will also enable the end-to-end quantum security to be realized. So our vision for the platform is to a nationwide collaboration platform for the field test bed for quantum safe communication, and it will be used for the pilot infrastructure, that test bed of quantum safe network that accessible for partner to perform field trial and proof of concept technology evaluation. We also would like to build up the security framework for in-depth security evaluation for quantum communication equipment and to see its certification. We also built up the reference guideline or the local standard to support the deployment and the use of the quantum safe technology. So in summary, the testbed, security lab, ecosystem, standardization are the keywords of our platform. So here is an illustration for how our NQSN network looks like. So in the territory metropolitan area network, we are going to use Singapore fiber infrastructure, and our target is to have the hybrid solution with QKD and PQC, and this is our short-term goal. The mid-term goal is also to have the quantum satellite to be part of the network, and our network mainly connected to the academic and private industry network partners. Another direction is on the quantum security lab. For this lab, our vision has mainly three directions. First is on the security evaluation of quantum communication, implementing by prototyping and modeling, and some testing and evaluation to exploring the quantum hacking attacks and the functionality validation. Third one is the joint lab capability with industry partner for certification and as well as the research lab expertise development. Besides that, we also engage in the standardization work at the local and the international scale. For the local standardization initiation for the quantum communication, there's the task force has been set up for the quantum communication network under the local authority IMDA, and local standards are being built up taking reference of the international standard. On the other hand, we would like also contribute and collaboration and support international standardization efforts for the quantum communication. So to summarize our activity here is that NQSN try to build up an ecosystem. On the upper part, it's the test bed, the performance evaluation, and end-to-end application, and to support the ecosystem build up. And the bottom part is on the quantum security evaluation and standardization to have the ecosystem to support the quantum communication and the quantum safe communication to be integrated in the ICT world. So this is pretty much my talk for today. And if you want to know our activity in National Quantum Safe Network Singapore, you can visit our website for more information.
Thanks for your attention. I would like to thank the organizer the invitation again. Thank you.